Can you believe it? This is going to be the last pre-calculus lesson I teach you forever. Okay, here we go. You're going to notice that honestly, today is just sigma notation, and it's similar to what we did last week. It's just like starting in a different form and then like ending into what we did last week. So the notation just looks different. So sigma notation is when we use the Greek letter sigma, and you can see it here. It looks like an E, and it's used to indicate a sum. So whenever you see sigma, it means sum. So the key is knowing what this whole notation is all about. So you're going to see the sigma. The number on top is the term you're ending at. So we're ending at term number 5. On the bottom is where we're starting. So we're going to start when n equals 1, and we're going to go until n equals 5. The pattern we're using is n squared, and this can be anything. So the way we would read this is the sum of n squared as n goes from 1 to 5. To write it out in expanded form, we would simply be replacing that n in our pattern part with the numbers 1 through 5. So we would do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And of course, there's an addition sign in between all of this because sigma means sum. So we could see that this would equal 55 because 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. When you add it all up, you get that it equals 55. So you can see that we can have our geometric series and sequences with sigma notation. So our first example here, ignore the numbering. I took out some because they were arithmetic sequences, and we haven't done that. So the numbering is off. Yes, I know. But our first example here says to write the sum of 4 times 2/5 times the n minus 1 power as n goes from 1 to 4 in expanded form. So we're going to replace our n with 1 through 4. So 1 minus 1 gives me 0 as my exponent. Then when I plug 2 in, 2 minus 1 gives me 1. Then when I plug 3 in, 3 minus 1 gives me an exponent of 2. And our ending number was 4, and 4 minus 1 is 3. When you put this in a calculator, our first term is 4, our second term is 8/5, our third term is 16 over 25, and our fourth term is 32 over 125. So this is how many terms are in this series. There's 4. 1, 2, 3, 4. It is a geometric series. Our R value is 2/5. If you were to do 8/5 divided by 4, you'd get 2/5, or you could do 16 over 25 divided by 8/5, you would also get 2 over 5. So same thing that we were doing last week. Notice in our pattern here, the part after the sigma sign, this 2/5, this number here happens to be the common ratio. So it's kind of like a hint there. It's our R. So we can find the sum. And again, we did this last week. So here's a refresher of the formula. We're finding the sum of all 4 terms. We said there was 4 terms. And yes, of course, you could just add them all up, and you'll see that here in a calculator. And you can see that work being done here. But you can also check to make sure when you put it in this formula, that you also get this number. So our first term was 4. We found that here when we did 4 times 2/5 raised to the 0 power. Our R was 2 over 5. So when you plug everything in, you should get 812 out of 125. Here's your answer. All right, let's try another example. All right, here's example 4. So first thing it wants us to do is write the sigma notation out in expanded form. So we're going from -2 to 3. So wherever n is, we're going to put -2. Then we'll put -1, then 0, then 1, then 2, then 3. When we put this in a calculator, you get the numbers underneath. 100 plus 20 plus 4 plus 4/5 plus 4 over 25 plus 4 over 125. So you can see there was 1, 2, 3, 4, 5, 6 terms in this series. Again, it is a geometric series. You should see that your common ratio is 1/5. If you did 20 divided by 100, you get 1/5, or 4 divided by 20, you get 1/5. Regardless what two terms you divide, you will see that your R is 1/5. So now we can find the sum. Again, we know that we're adding up 6 terms, so we're finding S sub 6. Our first term is, and that should say 100, not 10. Let me change that. And then you're going to do 1 minus, your R is a 1/5 to the 6th power, because you have 6 terms, all over 1 minus 1 to the 5th. And again, you could type this entire thing that I'm circling here into your calculator, and it'll give you the answer. So that'll be what all 6 terms would sum to. All right, last example. It says to write this sigma notation in expanded form, and we're going from 1 to infinity. So this is an infinite geometric series. It's because of this right here. We don't have an ending. It's not a finite geometric series. It's infinite. It's going to go on forever. So when it says how many terms are in the series, there's an infinite number. It's going to go on forever and ever and ever. So we can begin by plugging in for our expanded form that, we would start with 1, then go to 2, then 3, and we would do this forever and ever and ever. So we have, to start, we have 3/2 plus 3/4 plus 3/8. So we can see if we do 3/4 divided by 3/2 or 3/8 divided by 3/4, you should see that your common ratio is a 1/2. And remember from last week, if you get that common ratio on an infinite geometric series is between -1 and 1, which a 1/2 is, then we know it converges. So we can find a sum. Again, from last week, we have this formula here. So when we're trying to find the sum of an infinite geometric series, we do our a sub 1, which we saw here was 3/2, all over 1 minus r, which is a 1/2. So when we do that, we get a 3/2 divided by a 1/2, which ends up just being 3. So this series is going to converge, get really, 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 really close to 3. And that concludes your last lesson. I am going to make you guys one more video, so make sure that you watch that later in the week. And if you need anything or want to come say hi and bye and all that, feel free. I shall talk to you guys later. Let me know if there's anything I can do. If you are behind on work, feel free to get caught up. And again, if there's anything I can do, please do not hesitate to reach out. I miss you all so much.